Today, I will be solving some problems on material balance in mineral processing. I have given the necessary concepts that are required to solve these problems. However, for the detailed reading, you see the references which I had given in the lectures and update yourself. So, with that, let me take the problems on material balance in mineral processing. Now, as such, the first problem is a flotation plant treats feed whose grade is 0.8% copper. The plant produces concentrate and tailings. The copper grade of concentrate is 26% and that of the tailing is 0.16%. Now, calculate copper recovery in concentrate, fraction of feed in the concentrate and C enrichment ratio. Problem number 2, there is a ball mill circuit which employs rod mill and board mill for typical milling operation is shown, and the problem is as follows. In the circuit shown below, the dry solids of density 3000 kilogram per meter cube are fed at the rate of 25 tons per hour. The feed to the cyclone contains 36% solids by weight. It is found that 250 micron meter size in the rod mill discharge, ball mill discharge and cyclone feed is 27%, 5% and 14% respectively. That is what has been done. All the particles which are of 250 micron meter, they have been analyzed in the feed as well as in the discharge and ball mill discharge, rod mill discharge and cyclone feed, and their percentage are given. Determine the volumetric flow rate of feed. Feed means solid plus water, that is you have to find out the flow rate of water as well as that of solid. Problem number 3, a hydrocyclone produces two products. Now, as I said, the hydrocyclone, it separates feed into overflow and underflow. So, again here two product formula has to be used. A hydrocyclone produces two products, that is underflow and overflow from the feed. The overflow is treated further for concentration of valuable mineral, whereas underflow is recirculated. In a hydrocyclone, a slurry of density 1140 kilogram per meter cube is fed for separation. It produces underflow of slurry density 1290 kilogram per meter cube and overflow of slurry density this one. Determine mass flow rate of feed to the cyclone when 3 liter sample of underflow takes 4 seconds. Density of dry solid is given to you. Fourth problem, analyze the following circuit and determine the unknowns. Now, here the circuit is given. In the circuit what is done? Feed 1000 tons per hour, 10% lead sulphide, that is here mineral grade is given. Concentrate and tailing are given and you have to find out concentrate flow rate and flow rate of tailing. Problem 5th, in a hydrocyclone, a slurry containing 30% solid is fed for separation of coarse into fines. You can call coarse as underflow and fines as overflow, because overflow will be taken for further concentration operation, that is to recover the particle containing minerals. The underflow has 50% solids and the overflow has 15% solids. If the feed enters at 20 tons per hour in the hydrocyclone, calculate the tonnage of solid per hour in underflow. Problem 6, a plant treats 210 tons of material in a shift of metal grade 40% and tailing as metal grade 0.2%. Calculate mass of concentrate and tailing. 7, a flotation circuit consists of rougher, cleaner circuit to concentrate lead sulphide in feed as shown below. If rougher and cleaner, the grade of lead sulphide in feed is 15% and is delivered at 1200 tons per hour. The grade of cleaner tailings is 20%. The cleaner tailings are recycled to rougher and its circulating load is 0.25. The recovery and grade in the concentrate is 98% and 89% respectively. Calculate the flow rate and grade of the respective streams. And the last slide gives the answer for the various questions. Now, I will take question one by one. So, let me take now the question number 1. Say now solutions, but again I will appeal to all of you that please see the solution after you have attempted yourself. Now, this problem is as follows. So, we have a flotation plant. This is a flotation plant. And in the flotation plant, you have mass of feed, and where F percent or fraction is the grade of the feed, and you have mass of the concentrate, and C is the grade, and mass of the tailing, and T as the grade. You can take percent or fraction. So, simple mass balance MF MC plus MT and MF rather M capital F into F, that is equal to MC into C plus MT into T. That is what we have done in the conceptual presentation, and then we can straight away find out from here that MF upon MC, that is equal to C minus T upon F minus T. So, therefore, the plant recovery that is equal to MC into C upon MF into F, that is equal to 100, or we can also find out the recovery from, as I have derived this particular formula, F minus T upon C minus T. So, now we will substitute the values, say recovery that is equal to say 26 into 0.9 minus 0.16 divided by 26 minus 0.16 into 0.9, that is into 100. So, the recovery is 82.73%. That is the answer for this. Now, then you have to calculate fraction of feed in the concentrate. So, this is the A part. The B part, fraction of feed in the concentrate, you have to find out this ratio, and that is equal to F minus T upon C minus T. So, if we substitute the values 0.9 minus 0.16 upon 26 into 0.16, and that gives you 0.0286. That is the answer for part B. Now, you see that the concentrate is hardly of 2% in the 2% of the feed. So, a large amount of tailing is produced. The message that I want to give from here is that one of the important consideration in metal extraction is upgrading the ore in the mineral beneficiation, and as a result of upgrading you produce a large amount of waste, and that point is to be understood. Now, enrichment ratio this simply becomes what is the grade of the concentrate and grade of the feed. So, that will be equal to 26 upon 0.9. So, the enrichment ratio is 28.9. That is the answer for C1. Now, let us see the problem number 2. Problem number 2 is as such. Say we have, if this is the circuit, here is the feed, you have 25 tons per hour. You have here rod mill, and from here it goes to hydrocyclone, that is was given to you, and hydrocyclone it separates underflow, overflow, and underflow it enters into ball mill, and that is further goes to the hydrocyclone for separation, and here water is also added, water can be added. So, the problem says 25 tons per hour, and this goes to flotation, well whatever concentration operation. So, straight away we have to do the mass balance, that is the cyclone feed that is equal to ball mill feed, let us take it equal to B, and plus rod mill feed. That is what it consists of. So, cyclone feed, let us take it is equal to Cf. So, we are given the values. So, Cf cyclone feed, that will be equal to ball mill feed plus we are given 25 tons per hour. This is our equation number 1. Now, let us perform balance on 250 micron meter size particles as they are given to us. So, simply again we will do that Cf into 14, that is equal to 5 into B plus 25 into 27. So, that is our equation number 2. Now, from this by equation 1 and 2, if you simplify, I will just leave on it to you. So, B that will be equal to 36.1 tons per hour. Now, we can find out the cyclone feed of dry solid. Say cyclone feed of dry solids, that becomes 61.1 tons per hour. That is what the answer. This is dry solid, right. Now, we have to find out also the volumetric flow rates of feed, and feed consists of solids as well as water. So, first of all we will find out the volumetric, feed of dry solid, that is volumetric flow rate. Volumetric flow rate of feed of dry solids, that is equal to 61.1, and 3 tons per meter cube is given to us the density. So, it becomes 20.36 meter cube per hour. Now, how will you find out the volumetric flow rate of water? Any clue? I am just writing and you think before I finish my writing. So, volumetric flow rate of water, that will be 64 upon 36, which is the dilution ratio, multiply by 61.1 and divide by 1, because 1 ton per meter cube is the density of water. So, we get the volumetric fluid, this is the density of water. So, volumetric flow rate will come 108.6 meter cube per hour. So, you see what all these problems in fact require is a clear cut idea of mass balance. You have to see from where the mass is entering and from where the mass is being out. Now, you have to aid in the mass entry from all sources. For example, in this particular problem, the cyclone feed was having rod mill plus ball mill. So, these things are to be kept in mind while solving this particular problem. Now, let us take the problem number 3. The problem number 3 says you have to find out the mass flow rate of feed to the cyclone. Now, here a clue is given, 3 liter sample of underflow takes 4 seconds of time. Now, why this is given? Because from this value you can find out the volumetric flow rate of underflow you can find out. Now, before we do that, you recall I have given the derivation for this type of problem. So, what will you do? First, we will find out the percent solid. We will find out say percent solids in the feed, then in underflow and in overflow, because percent solid is not given. Now, percent solids in the feed, that will be equal to 100 into 3000 into 140 divide by 1140 into 2000. Now, in that of underflow, this is 100 into 3000 into 290 upon 1290 into 2000, and in overflow this is 100 into 3000 into 30, it is divided by 1030 into just making a compartment. So, if I calculate, I am getting here percent solid 18.42%, here it will be 33.72%, and here it will be 4.37%. Now, why I calculated the percent solid? I calculated the percent solid simply because one can find out the dilution ratio. That is why I have determined the percent solid. So, now I can find out now say dilution ratio of feed well, I have already given the formula. So, feed that is equal to 4.42, dilution ratio of underflow, that is equal to 1.97, and dilution ratio of overflow that is equal to 21.88. So, once we have determined the dilution ratio, now we can find out say mass flow rate of underflow, that will be equal to the formula F into density of underflow into percent solid in underflow. Now, here naturally we have assumed that the density of the solid does not change in the underflow or overflow, it remains the same. So, if we solve it, that will be equal to 3 upon, I am just substituting the value that you can also do it, into 3600 upon 4 into 1290 into 0.3372. So, that gives 1172 kilogram per hour. Now, you have to find out also water balance on the cyclone. We do water balance on the cyclone by performing water balance on the cyclone. I am just straightway writing down say 4.42 into mf, that is equal to 1.97 into 72 plus 21.88 into MO. Now, we know that by mass balance we can replace MO. So, that will be equal to 1.97 into 1172 plus 21.88 into MF minus 1172. Since we know that the mass balance is MF, that is equal to MU, that is underflow, plus MO, and from here one can replace MO by MF, and that is what I have done it over here. So, we just solve it. So, we get MF, that is equal to 1336 kilogram per hour. That is the answer for this particular question. Now, the problem 4, it is very simple. So, I will skip it and I will see that you can solve this particular problem. It is simply a mass balance to find out the various unknowns. Now, let me take problem number 5th. Now, problem number 5th has, so this is this a sort of hydrocyclone. We are having the feed which is 20 ton per hour, having 30% solid, and you have overflow which is 15% solid, and we have underflow which is 50% solid. So, you have to find out if the feed enters at 20 tons per hour in the hydrocyclone, calculate the tonnage of solid per hour in underflow. So, you have to calculate tonnage of solid. Tonnage of solid requires to be calculated in the underflow. Now, again you have to proceed with the mass balance, that is 20, that is equal to MU plus MO or MU or MUF, whichever we want, that is input, that is equal to output. Now, water balance, we can perform water balance, and for water balance we have, as you recall, F dash S into MF, that is equal to U dash into MU plus V dash into MO, where I will write once again, though I put in the lecture F dash S, U dash and V dash, they are dilution ratio of feed, underflow and overflow. Now, we can calculate the dilution ratios, and the dilution ratios F dash S you can calculate yourself. So, that value is 2.33. For U dash, the dilution ratio of underflow, that is equal to 1, and dilution ratio of overflow, that is equal to 5.67. So, now I can calculate now MU upon MF from the dilution ratios, and this will be equal to 0.715. You can calculate yourself these values, because the formula everything is given to you, you know how to calculate. So, when you know this value, we know MF. So, tonnage of dry solids per hour in underflow, tonnage of dry solids in underflow, that will be equal to 14.3 tons per hour. So, that is the answer or the solution of this particular problem. Now, let us take the problem 6. Now, problem 6 again a very simple problem. It simply says a plant treats 210 tons of material in a shift of metal grade. This one concentrate has metal grade and telling metal grade is given, calculate mass of concentrate and telling. Now, that is very simple. So, you know that the ratio MF upon MC, that is equal to C minus T upon F minus T. So, that becomes 17.3. So, therefore, MC will be equal to 12.1 tons and MT, that will be equal to 197.9 tons. I mean, this problem you can do. I do not think this is a very tough problem, it is a very easy problem. Now, let me take the problem number 7. Now, in a problem number 7, a flotation circuit is given which consists of rougher and cleaner. Now, in fact, let me give you a little bit background of this flotation. Now, in case of flotation, what happens when the concentration, that is when the flow is very large, then the concentration is carried out in 2 stages, rather is carried out in several stages. The stages are say roughing, scavenging, and cleaning. It is done in 3 stages if the volume to be treated is very large enough. Now, in the roughing stage, what is done? In the roughing stage, this is designed to remove easily recoverable particles. The stage scavenging, in the scavenging stage what is done, the tailings, because roughing will produce concentrate and tailing. So, the tailings of roughing operation, they are used to recover the valuable mineral. Tailings of scavenging, they are worthless, they are no more recycled in the circuit. The third stage is the, that means the scavenging, let us say scavenging concentrate that is equal to middling plus unliberated valuable mineral. That means it has to be ground. So, the entire circuit, it looks something like this. Say for example, if this is the say operation, this is the feed, then it goes to scavenger, and scavenger tailings, they are discarded. Now, the concentrate is further subjected to grinding operation, as it contains some of the unliberated particle, and now this grinding, this is again taken to the feed, and from the concentrate, the feed, the concentrate rather, it enters into cleaning, that is the concentrate. There is a concentrate, here is the tailing. So, cleaning, they again to the cleaning, once we have from here the final concentrate, and the tailing of the cleaning, it may undergo to grinding operation. This is the tailing. So, this is how just a feed side information what is done in the flotation. So, this particular problem is based on this particular concept. So, in the problem what is given, so you have a roughing operation, this is roughing operation, and here the concentrate, let us say concentrated McR, it enters into cleaner, its grade is C into R, then we have from here the cleaner concentrate, that is what the problem says. We have cleaner concentrate, and cleaner concentrate, let us say its mass is MC and its grade is CC. Now, it is given say R, that is equal to 98% recovery, and grade is 89%. Then the cleaner tailings, these are the cleaner tailings, and cleaner tailings is given to us 0.25 is the load ratio into 1200, that is equal to 300 tons per hour is given to us. Now, this cleaner again undergoes the so called roughing operation, and so the cycle completes. In the roughing, the feed you have 1200 tons per hour and lead sulphide grade is 15%. Here you have rougher tailings, and this rougher tailing, let us consider this is MT into R, and its grade let us say is TR. TR is the grade of. So, we have to find out the flow rates and grade of the respective streams. Again simple a mass balance type of problem, input is equal to output. So, if you do Ruffers total mass balance, then this is equal to 1200 plus 300, that is equal to MT R plus MC into R, that is the equation number 1. Now, similarly we can do cleaner total mass balance, that will be equal to MC into R, that should be equal to MC into C plus 300, that is our equation number 2. So, similarly then proceeding further, we will do rougher lead sulphide balance, where the mineral grade is given. So, we can write down this one 1200 into 15 by 100 plus 300 into 20 by 100, that is equal to M T R into T R plus M C R into C R. This will be our equation number 3. Similarly, we can also do cleaner lead sulphide balance. Cleaner lead sulphide balance. So, that will be equal to M C R into grade, that is equal to M C C into concentration grade plus 300 into 20 by 100. So, if we solve all these equations, recovery R, that is equal to mass of PBS in cleaner concentrate divided by mass of PBS in feet into 100, that is the definition of recovery. So, if I substitute all the values, then from here I can find out the mass of concentrate in the cleaner, that will come out to be equal to 198.6. So, by equation 2 I can find out MCR, that will be equal to 498.6 tons per hour, and therefore, MTR, that will be equal to 1001.4 tons per hour. Now, by equation 4, I can get the value of CR, which is the metal grade of the rougher concentrate, that will be equal to 47.5%. The formula everything I gave you, and by equation 3, in which TR is the only unknown quantity. So, if I substitute all the values, then I will get TR, that will be equal to 0.316%. Now, one more thing that I want to say about the concentrate, because it is the concentrate that is the most important, and I have said that a concentrate it consists of metal plus gangue. Now, again I tell you very clearly, though I am writing the metal, concentrate does not contain the metal I am writing, because that concentrate will be used for extraction of metal. The concentrate in fact contains valuable mineral, of which we are interested in finding out the metal, because from the extraction purposes the oxygen or sulfur part of the valuable mineral is also a tailing or is also a gangue. That is why I am writing here metal plus gangue. Simply metal I am writing because the concentrate will be used to extract the metal, otherwise the concentrate does not contain mineral. So, that point is to be clear. Now, let us just quantify it. So, let us say if M is the metal grade of pure mineral, M is metal grade of pure mineral, C is the metal grade of concentrate. Now, I am analyzing the concentrate. So, now gangue in the concentrate will be how much? Gangue in the concentrate that will be equal to, because now M is the metal grade of the pure mineral and C is the metal grade of concentrate. So, M minus C has become gangue in the concentrate. So, that is equal to M minus C, that is the gangue in the concentrate. Now, similarly, I can find out gangue in the feed, gangue in the feed, that is equal to M minus F, where F is the metal grade in the feed. So, let us, so this M minus F that has become the so called gangue in the feed. Now, if I say M F that is equal to mass of feed, and M C that is equal to mass of concentrate, then recovery R G, that is recovery of gangue in the concentrate, recovery of gangue in concentrate, that will be equal to M C is the mass of concentrate multiplied by M minus C, which is gangue in the concentrate, divided by mass of the feed into gangue in the feed. That point it should be clear. That is what is most important from the evaluation of the concentrate, its quality of the concentrate and its separation efficiency. So, recovery of gangue in the concentrate, that is equal to into 100. So, we can also put it that is equal to M C 1 into M minus C upon M minus F into 100, where M C 1 is equal to M C upon M F, that is equal to fraction of feed reported in the concentrate, fraction of feed reported in the concentrate. Now, similarly, I can also find out the recovery of metal, also I can. So, the separation efficiency will be, the separation efficiency will be simply will be equal to R M minus R G. So, if I substitute the value of R M will be 100 into M C 1 into C upon F minus 100 M C 1 M minus C upon M minus F. So, I further simplify it. So, I will be getting 100 M C upon M F. I simply replace M C 1 by M C upon M F, that is equal to M into C minus F upon F into M minus F. So, that is the separation efficiency and the evaluation of the concentrate. Now, let me give a very simple problem to illustrate this. Now, let us consider concentration of tin oxide mineral SNO2 mineral in cassiterite ore. Now, it is possible to produce a concentrate of the following grade and recovery. following grade and recovery by utilizing different methods. So, what is given? Let us take it concentrate, then tin grade and recovery. Concentrate number 1, tin grade is 63% and recovery is 62%. Concentrate number 2, 42% and 72%. Concentrate number 3, 21% and 78%. Now, tin grade in feed, is, let us given 1%. Now, we have to find out the separation efficiency and analyze the result. So, what will I do? I will find out the separation efficiency. So, separation efficiency, that will be equal to 100 into F into R m upon C into 100. You can convert the formula in this way also, m into C minus F upon F into m minus F, because here recovery is given and the formula can be made in terms of the recovery. I have written in terms of the recovery, that is R m. Now straight away I can substitute the value. So, what I do now? I find out the separation efficiency for concentrate 1, that will be equal to 1 into 62 upon 63, 78.76 into 62 upon 1 into 77.76. Now, you may be wondering from where I am getting 78.76. Now, 78.76 is the metal grade of the pure SnO2 mineral. So, m, I can just do m, that is equal to 118.69, which is the atomic weight of tin, 118.69 plus 32. So, that becomes into 100, of course, 69, that is, and then it becomes equal to 78.76%. So, that is the metal grade of the pure mineral, that is from where this comes. So, the separation efficiency, that becomes, or that is equal to 61.8%. Now, in the similar way I can find out separation efficiency 2, that will be 1 into 72 upon 42 into 78.76 into 41 upon 1 into 77.76, that will be equal to 71.18%. I can find out now separation efficiency 3. We can do the substitution, answer will be 75.24%. Now, you can see from here that the separation efficiency in 3 is greater than separation efficiency in 2 and is greater than separation efficiency in 1. Now, naturally, one is tempted to go for the method which produces concentrate number 3, but here the most important thing also to see what is the tin grade in the concentrate. In the concentrate number 3, the tin grade is the lowest one. The tin grade in concentrate is 21% only. So, you can imagine the amount of gangue is very large as compared to concentrate number 1. However, the concentrate number 1 has a separation efficiency of around 61.8%, is lower than that of third one, but however, the grade of the tin is very high. Well, so in a way you have to meet a compromise, either to go for a very high recovery and compromise with the tin grade or metal grade, or go with the low recovery and high tin grade. That will depend upon the type of ore, the type of mineral, the methods to be employed, and so on and so forth. So, in fact, the objective of mineral beneficiation is to increase the metal grade of the ore. That is the main objective of the mineral processing. That is where we do the mineral processing to increase the grade of the ore. Now, it is in this attempt we have to lose or we have to sacrifice the recovery, because the more is the recovery, it is possible that you are bringing grade lower down. So, one is to compromise what should be the grade and what should be the recovery. That is what my objective of illustration of this particular problem.